Hello friends, welcome to my course on advanced engineering mathematics. We will first have the lecture on analytic functions. In order to define an analytic function, we need the concept of limit and derivative. We shall see that these concepts are similar to those in real calculus. First, we will define a function on a set S of complex numbers. By a function defined on a set S of complex numbers, we mean a rule which assigns to each z in S a unique complex number, say W. We then write W equal to Fz or simply Wz. The variable z is called a complex variable. The set z is called the domain of definition of Fz. The set of complex numbers which W equal to Fz assumes as z varies on S is called the range of values of the function W equal to Fz. Now, let us say that u and b be the real and imaginary parts of the complex number W. Then if you take z equal to x plus iy, we will have W equal to Fz equal to uxy plus ivxy, because z depends on x and y and W is a function of z. So, in general the real and imaginary parts of W, that is u and b, are functions of x and y, and we therefore write W equal to uxy plus ivxy. Now, by this we can say that a complex function Fz is equivalent to two real functions uxy and bxy, each depending on two real variables x and y. For example, let us consider W equal to Fz equal to z square plus 3z. Then here you can see uxy plus ibxy is equal to x plus iy whole square plus 3 times x plus iy. Now, we can write it as using iota square equal to minus 1, we have x square minus y square plus 2ixy plus 3x plus 3iy, and so we can write it as x square minus y square plus 3x plus iota times 2xy plus 3y. So, equating real and imaginary parts, then uxy is equal to x square minus y square plus 3x and bxy equal to 2xy plus 3y. So, you can see that the real and imaginary parts of W, that is u and b, are functions of x and y. Now, let us define a limit. A function Fz is said to have a limit L as z approaches to z naught if Fz is defined in a neighborhood of z naught equal to z naught, except perhaps at z naught itself. I mean, function need not be defined at the point z naught, and then if for every epsilon greater than 0, no matter how small, one can find a positive real number delta depending on epsilon, such that for all z not equal to 0 in the disk, mod of z minus z naught less than delta, mod of Fz minus L is less than epsilon. This means that mod of Fz must be less than epsilon. In the deleted neighborhood, 0 less than mod of z minus z naught less than delta. See, you take the complex plane. If z naught is a point here, then you construct an open circular disk with center at z naught of radius delta. Then the open circular disk is mod of z minus z naught less than delta. Now, we are considering the set of all z such that mod of z minus z naught is less than delta, but z is not equal to z naught. So, we write 0 less than mod of z minus z naught less than delta. This is called a deleted neighborhood of z naught. So, mod of Fz must be less than mod of Fz minus L must be less than epsilon in the deleted neighborhood of z naught, that is 0 less than mod of z minus z naught less than delta, which means that the values of Fz are as close as desired to L for all z which are sufficiently close to z naught. Now, in mathematically we can write it as limit z tends to z naught Fz equal to L. Now, you can note here that z can approach to z naught from any direction in the complex plane. In the real calculus, we have only we have to move along a line. When we say that x approaches to x naught, then either we approach x naught from left or we approach x naught from right, but in the case of complex z naught lies in the plane. So, z can approach to z naught from any direction. So, this has to be kept in mind while taking the limit. Now, then the limit of f z as z tends to z naught exists and it is unique. So, let us prove this. Limit of f z as z tends to z naught exists if limit z tends to z naught f z exists, then it is unique. So, to prove this, let limit z tends to z naught f z be equal to L1 and limit z tends to z naught f z be equal to L2. Then we have to show that L1 is equal to L2. So, let us take any epsilon greater than 0 . Then by the definition of limit, for a given epsilon greater than 0, we can find a positive number, say delta 1 greater than 0, such that mod of f z minus L1 is less than epsilon by 2 whenever 0 is less than mod of z minus z naught less than delta 1. This is because limit of f z as z tends to z naught is equal to L1. Now, since limit z tends to z naught f z equal to L2, again by the definition of limit, for the same epsilon greater than 0, there exists delta 2 greater than 0, such that mod of f z minus L2 is less than epsilon by 2 whenever 0 is less than mod of z minus z naught less than delta 2. Okay. Now, let us say this is equation 1, this is equation 2. So, now let us define, let delta be the minimum of the two positive numbers delta 1 and delta 2. Then for all z satisfying uh, 0 less than mod of z minus z naught less than delta, we will have mod of f z minus L1 less than epsilon by 2 and mod of f z minus L2 less than epsilon by 2. Okay. Now, let us apply triangle inequality. So, by triangle inequality, mod of L1 minus L2, mod of L1 minus L2 is less than or equal to mod of f z minus L1 plus mod of f z minus L2, and each one is less than epsilon by 2 in the common neighborhood, that is 0 less than mod of z minus z naught less than delta. So, for all z satisfying 0 less than mod of z minus z naught less than delta. Okay. So, what we have mod of L1 minus L2 is less than or equal to epsilon, okay, in this neighborhood. Now, since epsilon greater than 0 is arbitrary, epsilon greater than 0 is arbitrary, we can take it as small as we please. Okay. So, we have L1 equal to L2. So, this is how we show that if the limit of fz as z tends to z naught exists, then it is unique. Okay. Now, let us define the continuity of a complex function fz. A function fz is said to be continuous at z equal to z naught if fz naught is defined and limit of fz as z approaches z naught equals fz naught. The function fz is said to be continuous in a domain if it is continuous at each point of that domain. Then we come to the concept of differentiability. A function fz will be called differentiable at a point z equal to z naught if the limit of f z naught plus delta z minus f z naught over delta z as delta z approaches 0 exists. This limit is then called the derivative of fz at the point z equal to z naught, and we denote it by f prime z naught. Now, if you put here z for z naught plus delta z, then you can see that delta z is z minus z naught. So, this quotient will become f z minus f z naught divided by z minus z naught, and when z tends to z naught, delta z goes to 0. So, delta z goes to 0 will be replaced by z goes to z naught. So, an alternative definition for the derivative of a complex function at the point z naught is f prime z naught equal to limit z tends to z naught f z minus f z naught over z minus z naught. Now, let us note that the differentiability at z naught means that along whatever path z approaches z naught, the quotient f z naught plus delta z minus f z naught over delta z approaches a certain value, and all these values are equal. This fact is very important here. Now, let us look at the function f z equal to z square and show that it is differentiable for all z and f prime z is equal to 2z. Okay. So, let us find the limit of f z plus delta z minus f z divided by delta z as delta z tends to 0. If this limit exists, then we shall say that the derivative of f z exists, and whatever is this value, that will be the derivative of f z at the point z. So, we are finding the derivative of f z at the point z here. So, this is limit delta z goes to 0 z plus delta z whole square minus z square divided by delta z. Okay. So, this is equal to limit delta z tends to 0 z square plus delta z whole square plus 2z delta z minus z square divided by delta z. Okay. So, z square will cancel, we divide by delta z and get limit delta z tends to 0 delta z plus 2z. Okay. When delta z goes to 0, delta z plus 2z goes to 2z. So, we can say that the limit of f z plus delta z minus f z over delta z as delta z goes to 0 exists and is 2z, and thus by definition of the derivative f prime z, by definition of the derivative f prime z is equal to this limit. So, f prime z is equal to 2z. So, function is differentiable and f prime z is equal to 2z for all z belonging to the set of complex number C. Now, let us come to another example, f z equal to z conjugate. Okay. We shall show that this function is not differentiable for any z, okay, although it is continuous for all z. We can see its continuity also. Suppose you want to show the continuity of z conjugate, then what you do, consider we can show that limit of f z as z goes to say some z naught, okay. Z goes to z naught is equal to f z naught, okay. If you want to show the continuity of this function f z equal to z conjugate, then we have to show that limit of f z as z goes to z naught is equal to f z naught. That is to that. So, for this to prove, what do we do? Let epsilon be greater than 0, okay. Then consider mod of f z minus f z naught. This is equal to mod of z conjugate minus z naught conjugate, okay. And this is equal to mod of z minus z naught whole conjugate, okay. But mod of z minus z naught conjugate is equal to mod of z minus z naught, okay. So, mod of f z minus f z naught is less than epsilon whenever this is less than epsilon whenever mod of z minus z naught is less than delta and 0 less than delta less than or equal to epsilon. So, suppose epsilon is greater than 0, then you can take any delta which is positive, but less than or equal to epsilon. We shall always have mod of f z minus f z naught less than epsilon, because mod of z minus z naught is less than delta and delta is less than or equal to epsilon. So, function f z is continuous at any z naught, okay. So, this hence f z is continuous for all z. Okay, now let us show that it is not differentiable. So, consider f z plus delta z minus f z divided by delta z. This is equal to, by definition, z plus delta z conjugate minus z conjugate divided by delta z. Z plus delta z conjugate is z conjugate plus delta z conjugate minus z conjugate, okay. So, this will cancel and you will get delta z conjugate divided by delta z. Now, if z is equal to x plus I y, let delta z be in delta x plus I delta y, okay. Delta x be equal to delta z be equal to delta x plus I delta y. So, delta z conjugate will be delta x minus I delta y divided by delta x plus I delta y, okay. Now, what we do is suppose this is your complex plane, here is the point z naught z and here is the point z plus delta z, okay. So, what we do, we first move down when we reach this z, okay, that is in this line parallel to x axis, okay. So, we move down parallel to y axis till we reach this point here, okay. So, this is, if this z is x y, this point is x plus delta x y point, okay. So, when we reach here, this is suppose P, this is Q, okay, and this is R. So, the coordinates of R are x plus delta x and then y, okay. So, when we reach this point R, we move towards the point P, because delta z is tending to 0. So, after delta y, this length is delta y, after delta y becomes 0, we reach the point x plus delta x y and then we move towards P. So, delta x tends to 0. So, after delta y becomes 0, delta x approaches to 0. If we move along path 1, let us say this is path 1, if we move along the path 1, okay, where we first move from the point Q to the point P along the line QR, which is parallel to y axis, and R is the point in the line straight line parallel to x axis passing through P. So, the coordinates of R are x plus delta x y. So, when we reach R, delta y has become 0 and then we are moving towards the point P, that is in the direction R P. So, delta x tends to 0. So, when delta y becomes 0, then delta x tends to 0. So, along path 1 the quotient approaches to we have f z limit delta z tends to 0, f z plus delta z minus f z divided by delta z equal to delta y has become 0. So, limit delta x tends to 0, delta x by delta x, and therefore 1. So, along path 1, okay, along path 1 limit of f z plus delta z minus f z over delta z as delta z goes to 0 is equal to 1. If we here we had P point, here we have Q point, and we are moving down parallel to y axis. This was the point z naught plus z plus delta z, here was the point z, and so if this z is x y, the Cartesian coordinates of P are x y, here the Cartesian coordinates are x plus delta x, y plus delta y, and this point R has coordinates x plus delta x, y, and this path we called as path 1. Along path 1 we have found the limit of f z plus delta z minus f z divided by delta z. Now, let us consider path 2 where we move parallel to y axis. From the point Q we move parallel to y axis, then what will happen, delta x will tend to 0. So, when delta x has become 0, that means we reach this point. The Cartesian coordinates of this point are x, y plus delta y. So, let us call this point as S. So, we have, so after delta x has become 0, this path let us call as 2. So, along path 2, after delta x becomes 0, when we move to P, what happens, delta y goes to 0. Okay. So, limit delta z tends to 0, f z plus delta z minus f z divided by delta z, which is equal to limit delta z tends to 0, delta x minus I delta y divided by delta x plus I delta y. This will be equal to limit delta y tends to 0 minus I delta y divided by I delta y, and what we will get, the limit will be minus 1. So, along path 1 the limit is 1, while along path 2 the limit is minus 1. Okay. So, the limit is not same, and therefore, limit z tends to 0, f z plus delta z, limit delta z tends to 0, f z plus delta z minus f z divided by delta z does not exist for any z, okay, for any z. And this means that f z equal to z conjugate is not differentiable for any z. Okay. So, we have seen that f z equal to z conjugate is continuous for every z, but it is not differentiable for any z. Okay. There is a result which says that if f z is differentiable at a point z equal to z naught, then it is continuous at that point. So, that result also we can prove here. Of course, converse is not true as we have seen here. So, let us prove that we can prove this theorem. The theorem is, if f z is differentiable at z equal to z naught, then it is continuous at z naught. So, let us prove this. So, let f z be differentiable at z equal to z naught, then limit z tends to z naught, f z minus f z naught divided by z minus z naught exists and equals f prime z naught. Okay. We have to show that f z is continuous at z equal to z naught. So, let us take we have to consider limit z tends to z naught f z minus f z naught. Let us consider this. If we can show that limit of f z minus f z naught as z tends to z naught is 0, then limit of f z as z to z naught will be equal to f z naught. So, this is equal to limit z tends to z naught f z minus f z naught divided by z minus z naught into z minus z naught. Now, since limit of f z minus f z naught over z minus z naught exists and equals f prime z naught, and limit of z minus z naught as z tends to z naught equals and exists and is equal to 0. So, limit of the product of this expression and this expression exists, and we have f prime z naught into 0. Okay. So, this is equal to 0. This means that limit of f z as z tends to z naught is equal to f z naught, which means that f z is continuous at z equal to z naught. So, any differentiable function is always continuous, but the converse is not true, as we have seen in the case of z equal f z equal to z conjugate. Now, let us look at the other rules of differential calculus. All the familiar rules of real differential calculus continue to hold in complex. Let us come to the concept of analyticity. A function f z is said to be analytic at a point z naught in a domain D if f z is differentiable in a neighborhood of z naught. So, the function f z is called analytic in D if it is analytic at all points of D. Now, you can note here that the analyticity of a complex function at a point z naught is not the same as the differentiability at a point. Analyticity at a point is a neighborhood property. For the function to be analytic at a point z equal to z naught, the function has to be differentiable in a neighborhood of z naught. So, so that is the difference. A function which is analytic in D is also called regular in D or holomorphic in D. Let us say, for example, f z equal to c naught plus c 1 z plus c 2 z square and so on, c n z to the power n, where c naught, c 1, c 2, c n are complex constant. This is a polynomial in z, and so it is analytic for all z. It is differentiable for all z, and therefore, it is analytic for all z. If you look at the function f z equal to 1 over 1 minus z, we can see that it is not defined at the point z equal to 1. Okay. And so, then for all other points z, we can find its derivative f prime z is equal to minus 1 over 1 minus z whole square into minus 1, that is 1 over 1 minus z whole square. So, for all z not equal to 1, the function f z is differentiable, and therefore, we can say that it is analytic for all z except z equal to 1. Let us look at the function fz equal to rz. Rz means real part of z, or fz equal to imaginary part of z. We can see that they are not differentiable for any z. For example, let us consider fz equal to rz. So, if z is equal to x plus iy, then real part of z is equal to x. Okay. So, fz will be equal to x. We want to show that fz is not differentiable for any z. So, let us consider fz plus delta z minus fz divided by delta z. We will take the limit of this as delta z goes to 0 and show that this limit does not exist. So, when z is x plus iy, delta z let us take as delta x plus I delta y, so that z plus delta z is equal to x plus delta x plus I by plus delta y. So, real part of z plus delta z, this is equal to real part of z plus delta z by definition minus real part of z divided by delta z, and real part of z plus delta z is x plus delta x, okay, minus real part of x z is equal to x divided by delta z. So, this is equal to what? Delta x divided by delta x plus I delta y. Okay. Now, again what we do, this is your point P and here is the point Q. Okay. So, this is z point, this is z plus delta z complex number. We move along the path 1, that is parallel to y axis, reach the point R. So, this is your point x plus delta x y. Okay. So, after delta y has become 0, when we move to the point P, delta y will tend to 0. Okay. So, after delta y becomes 0, when we move to P, when we move to P, delta x tends to 0. So, then limit of delta x divided by delta x plus I delta y as delta x goes to 0, this will be equal to limit delta x tends to 0, delta x divided by delta x, which is equal to 1. And when we move along this path, okay, along this path, so after delta x has become 0, we reach this point S. Okay. These coordinates of this are x, y plus delta y. So, then delta y will tend to 0. So, along path 2, after delta x becomes 0, we have limit delta y tends to 0, delta x over delta x plus I delta y equal to limit 0 divided by delta x has become 0, 0 plus I delta y. This is equal to 0. So, along path 1, the expression f z plus delta z minus f z over delta z goes to 1, while along path 2, f z plus delta z minus f z over delta z goes to 0. So, limit delta z tends to 0, f z plus delta z minus f z divided by delta z does not exist. And therefore, f z equal to real part of z is not differentiable for any z. Similarly, we can show that f z is equal to imaginary part of z is not differentiable for any z. Now, let us show that f z equal to mod of z square is a function which is differentiable only at z equal to 0 and nowhere else, and this means that we can conclude that f z equal to mod of z square is not analytic at any point. Even at z equal to 0 it is not analytic, because it is not differentiable at any point other than z equal to 0. For analyticity at z equal to 0, we need a neighborhood of z equal to 0 in which it is differentiable. Okay. So, let us show that it is differentiable only at z equal to 0. So, let us consider f z plus delta z minus f z divided by delta z, and take the limit of this as delta z goes to 0. So, when f z is equal to mod of z square, f z plus delta z will be mod of z plus delta z whole square. So, we will have okay. Now, we know that if z is any complex number, if z is equal to x plus I y, then z conjugate is x minus I y, and z into z conjugate is equal to x square plus y square, which is equal to mod of z square, because mod of z is equal to under root x square plus y square. Okay. So, z conjugate is equal to mod of z square. So, we can write here limit delta z tends to 0, z plus delta z into z plus delta z conjugate minus z into z conjugate divided by delta z, which is equal to limit delta z tends to 0, z plus delta z into z conjugate plus delta z conjugate minus z conjugate divided by delta z. Now, this is equal to z into z conjugate, z into delta z conjugate, then delta z into z conjugate, then delta z into delta z conjugate minus z conjugate divided by delta z. Now, this expression, this term will cancel with this, and we will have then you see this dividing by delta z, we have z times delta z conjugate divided by delta z plus z conjugate plus delta z conjugate. Okay. Now, here we can see that we have already seen that limit of delta z conjugate divided by delta z when delta z goes to 0. We have already seen that limit of delta z conjugate over delta z as delta z goes to 0 does not exist. While proving that f z equal to z conjugate is not differentiable for any z, we have shown that limit of delta z conjugate over delta z as delta z goes to 0 does not exist. So, if z is not equal to 0, if z is not equal to 0, this limit will not exist. Okay? Limit of delta z conjugate over delta z. If z is equal to 0, this term will become 0. So, this term will not disappear. Okay? But if z is not equal to 0, then if z is not equal to 0, then limit of delta z goes to 0, f z plus delta z minus f z divided by delta z does not exist, as the limit of delta z conjugate over delta z as delta z goes to 0 does not exist. Okay. See, when delta z goes to 0, if z is not equal to 0, this term, this does not have the limit. This term is independent of delta z. So, this will remain z conjugate, this term will go to 0, when delta z goes to 0, delta z conjugate also goes to 0. So, with this term and this term there is no problem, but with this term there is a problem if z is not equal to 0, and if z is not equal to 0, therefore, the limit of f z plus delta z minus f z over delta z as delta z goes to 0 does not exist. So, in case z equal to 0, then we have f limit delta z goes to 0, f z plus delta z minus f z over delta z equal to limit delta z goes to 0, f z equal to 0, this term becomes 0, we have z equal to 0, so z conjugate is also 0, so we have simply delta z conjugate. Okay. So, when delta z goes to 0, delta z conjugate also goes to 0, so we have the limit 0, and so the function f z equal to mod of z square is differentiable only at 0 and nowhere else. So, it is not analytic at any point. With this, I would like to end my lecture. Thank you very much for your attention.